Good morning, everyone. So let us start. Today we will be summarizing week 11 content. So have you watched week 11 videos? Class, have you watched week 11 videos?
Yes, ma'am.
All right, that's nice. So let us start. The first thing we will be discussing is Fourier transform for circuit analysis. So in particular, we will be discussing about with respect to RLC circuits. Circuits which only have resistor, inductor, or capacitor along with battery or current source. Mm. So now let us write the impedance in RLC circuits. Suppose we have a resistor. So how can we write the voltage across the resistor? Ohm's law. So VRT is equal to R times IT. Can we say that?
Yes, ma'am.
Now let us convert it in Fourier domain. So I will have V R J omega. R is a constant, it stays as it is, and IT will convert to its Fourier transform I of j omega. Now, similarly, let us do this for capacitor. So, for capacitor, V is Q by C, and and Q is the integral of the current. So, we have this minus infinity to T. This is clear for the equation for capacitor.
Yes, ma'am.
Now, let us write it in Fourier domain. Now, when we integrate some function, so we get two terms in the Fourier domain. One is this 1 upon c j omega I of j omega, and we get another term which is pi times I of 0 delta omega. So this is as per the property. Now what we will do is we will we will take current to be zero before we turn on the circuit. I'll write it here. Zero if current before turning on circuit is equal to zero. So uh, 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 at t equal to zero, sorry. Zero if current before turning on circuit. I mean, what I want to say is that before we turn on the circuit, the current is zero. It flows only after the circuit is turned on. So my this second term goes to zero. So what I'm left with is VCj omega 1 upon Cj omega Ij omega. The second term has gone to zero. Now let us bring this j in the numerator. So what I will have is minus j upon omega c I of j omega. Basically, here we did multiplication and division by j, and we got this. This is clear.
Yes, ma'am.
Others are also understanding, na? Sudali, Rohit, Jay.
Yes, ma'am.
Okay, now let us write the same for inductor. So in the voltage for inductor is L di by dt. Now let us write it in Fourier domain. So I will have VL of j omega is equal to L. For derivative, j omega comes in the Fourier transform. So I have these. Now, if we look at this, the resistor one, the capacitor one, the inductor one, we see that the voltage is some impedance Z times the current. So let us write it down. V of j omega is Z times I of j omega. Z is the impedance. Now we can represent Z is a complex number. So we can, because here there is, in the resistor, there is this real component. Then in capacitor, there is J, inductor, there is J. So in general, Z is a complex number and we can write it as A plus JB. Z is equal to A plus JB. When B is less than 0, we'll look at this capacitor. B is less than 0, there is this negative sign. That means I have capacitor. If B is greater than 0, look at the inductor, it is positive. So that means B greater than 0 corresponds to inductor. And if B is equal to 0, the first resistor case, I have uh, a resistive circuit. So this was some of the basic about RLC circuit. Now let us solve one example. I will not solve it completely because it is just the same which was there in the lecture. So let us quickly see. This impedance is Z1. This is a voltage source. Voltage in time domain is X of t. Then we have another impedance Z2. Another here Z3. And finally Z4. So input voltage is X of t. We are asked to find output voltage across Z4 and frequency response. Output voltage across Z4 and frequency response. This is what we have to find out. So what we will do is we will convert it to Fourier domain, calculate the things in Fourier domain, and if time domain things are asked, then we can always take the inverse Fourier transform. So this will become X of j omega. We are taking the output across Z4. So in time domain, it will be Yt. In the Fourier or frequency domain, it will be Y of j omega. In the first loop, I will take the current I1 j omega. In the second loop, I2 j of omega. Now what we will do is we will use KVL for first loop, second loop, and for this relationship between Yt and Z4. And from solving these equations, we will get the answer. Would you like to solve it now?
Okay.
You want to solve now, Ananya?
Yes, ma'am.
Okay, so if you want to solve, take 3 minutes. You start solving. I'm just writing the three equations. Or maybe let me first explain how we are writing the equations and then you can solve. So let us consider this first loop, this one. Applying KVL, X of j omega is equal to Z1 I1 j omega plus Z2. Across Z2, there are two currents in different directions. So we will take I1 minus I2 because we are in loop 1. I1 j omega minus I2 j omega. So this is what we get for the first loop. This is equation number 1. Now let us consider this second loop. There is no voltage source inside, so the total voltage will be 0 in this loop as per KVL. So 0 is equal to Z3 I2, and across Z4 also we have I2, and now Z2, again two currents opposing directions. We are in loop 2, so we will take I2 minus I1. I2 j omega minus I1 j omega. This is my second equation. For the third equation, I will just write this input-output relation. So I have y of j omega is equal to I2 j omega Z4. This is my third equation. Now, if you want to try, then try and solve and give me the expression for h of j omega. H of j omega will be equal to y of j omega upon x of j omega. If you want to solve, please solve, but I'm not going to solve it here. You can watch that in the lecture. It is just same as that. I will just give you the final expression. If you want to solve, please go ahead. Take 3 minutes. Are you solving?
Yes, ma'am.
All right.
Ma'am, this calculation will go too much, so we can write I2 j omega as minus Z2.
So what you can do is now from equation 1, uh, write I1 in terms of I2. Then in equation 2, substitute I1. Then you will get everything in terms of I2. Then in third equation, when you substitute I2, you will get a relation in terms of j omega and x of j omega. And then if you divide, then you will get this expression.
Yes, ma'am.
I'm writing it down over here. Z2 Z4 upon Z1 plus Z2, Z2 plus Z3 plus Z4 minus Z2 square upon Z1 plus Z2 inverse. So this is what you will get. Now the next thing that we have to discuss is sampling. There was a problem based on sampling. So let's quickly see sampling very briefly, although. So what we have is a signal xt. It is multiplied with impulse train. Xt multiplied with impulse train. And we want to find when xt is multiplied with impulse train, we will get a discrete time signal. And we want to find the spectrum of this sample discrete signal. So I have xt and it is multiplied with this impulse train, which is represented like this: minus infinity to infinity n of t minus delta t. So I will call this as zt. I will draw zt for you here. This is zt time t. When n is equal to 0, I have 1 at t equal to 0, then capital T, 2 capital T, 3 capital T, and so on. And similarly on the negative side. So 0, capital T, 2t, 3t, minus 2t. This gap you see over here, this is capital T. Now let us just take any arbitrary xt just to show you how the multiplication looks like. So suppose xt is something like this. Now when we multiply these two, what will we get? Class, when we multiply zt and xt, what will we get?
It will be this same zt, just with the amplitude multiply.
Yes. So we will have the same impulses but with some scale factor and that will correspond to xt. So what I will have is now, like at t equal to 0, I will have this sample, this one over here, and the amplitude will become the one of xt at t equal to 0. Then next, I will have next sample at t equal to t, next at t equal to 2t, then 3t, and so on. And similarly here. So earlier xt was a continuous time signal, but once we multiplied it with impulse train, we get a discrete time signal. Uh, so this is how xt will look like. Let us call it maybe x dash. I mean, it will be a discrete signal, not a continuous one. So this is how my sample signal is going to look like. And I want to find the spectrum of this. That is, I want to find how this is going to look in the frequency domain. Since we just have any arbitrary signal xt, so we basically want to look at something called Nyquist theorem and aliasing, and a little bit of ADC and DAC. So this process now where we converted this continuous time signal to discrete time signal, we can call it as analog to digital conversion. So this is my sampled signal. It is a discrete time signal. Now in time domain now we multiplied them. So when we go to frequency domain, there will be convolution of the Fourier transform of these two. So first let us write down the Fourier transform of the impulse train. Again, I'm not going to solve that. That was there in previous lecture, so you'll have to refer that. This is the impulse train ZT. When we find the Fourier transform, we get 1 upon T sigma n equal to minus infinity to infinity delta omega minus n omega naught, and here omega naught is equal to 2 pi by T. So how will z of omega look like? I will draw it here. If this is zt, then the Fourier transform z of omega will look like this. Omega over here, z of j. Class, you're following now?
Yes, ma'am.
All right. So at t equal to 0, at omega equal to 0, I will have one impulse. Then the next one will be at omega naught because this is my function. Then next one, 2 omega naught, then 3 omega naught, 4 omega naught, and so on. Similarly, on the negative side, so minus omega naught, minus 2 omega naught, and so on. Now, since we want to find the spectrum of this discrete time signal, so what we had was x of t multiplied with zt, the impulse train, which was this. Now, multiplication in time corresponds to convolution in frequency, but there is the scale factor of 1 upon 2 pi. So I will have x of j convolved with 1 upon t. We are just writing down the this expression, Fourier transform of impulse train. All right, so delta of omega minus n omega naught. Now we took this arbitrary signal xt. Let us take an arbitrary Fourier transform, which is of the following form. So this I am calling as x of j omega. I have taken this in order to explain, right? This distance is, or this thing bandwidth, we can call it as b. Now look at this. When we convolve x of j omega with impulse, then convolution with impulse, we get the same signal with some delay or advance, whatever is there. So what I'm saying is we are going to get x of j omega convolved with delta of omega minus n omega naught will give me x of j omega minus n omega naught. So what we will have now, uh, this was x of j omega. There is this summation. So they are going to repeat. So basically, I will have repetition of this thing inside this red color. The spectrum will get repeated. And how will that be? I will show you. So this is how the spectrum is going to look like. Spectrum of the discrete time or the sampled signal. So this was the first copy centered around omega equal to 0. Next one will be centered around omega naught. Then the next one 2 omega naught and so on. And similarly in the negative side also. So this one is centered around omega naught. This one will be centered around 2 omega naught and so on. If we come to the negative side, This will be centered around minus omega naught. The next one around minus 2 omega naught. And it will just keep on repeating. So this is my spectrum. Now what I want, if I want to get back my signal xt from this discrete time signal, so we had this discrete time signal which looked like this in time domain, and uh, in frequency domain this is how it looks like. Now if we want to get back xt from this discrete time signal, then we will use a low pass filter. So if I pass it through a low pass filter, so it will be such that it will select this one, this copy, and rest of the copies will be removed because it passes these low frequencies and other higher frequencies will be attenuated or removed. And now we get back the spectrum x of j omega. We take the inverse Fourier transform, we get back xt. So here we see that there, like everything turned out to be fine. We got back our signal. Yeah, and this process of getting back the continuous time signal, that is digital to analog conversion. This is what basically happens. So this was the case where we did not see any overlapping. But if this B, if this B is less, if B is greater than omega naught, then we will have some overlap. So let us see that by taking some numbers. Suppose here I take this to be between minus 1 to 1 and omega naught. Okay, maybe I'll just, instead of taking numbers, I'll just quickly draw and show you what happens in the case of overlap. This overlap is also called aliasing. So let me draw the repeated samples with some overlap over there. This is the first copy. Now my second copy comes like this. This was the overlap I was talking about. Like this. Then this overlaps with the next one, and so on. And similarly on the negative side. Class, you're following now?
Yes, ma'am.
So when we have overlap, and if in this overlap I apply low pass filter, will I get back xt? No, I will not get back because these extra things will be passed and that will not give me xt back. So if I apply low pass filter over here now, I will in fact get something like this. Something, this kind of a shape which will not give me my xt back. Maybe we'll get something like this. And if we find the inverse Fourier transform of this, that will not be xt. So this is what happens in overlapping. So what we want is this omega naught, this gap should be greater than this B to avoid this overlap. I will just write it down. Omega naught should be greater than B to avoid aliasing. And this comes from, there is something called Nyquist sampling theorem, which very well says how we can recover our signal. I mean, the freak condition that should be there. But I think this will be covered in DSP. So right now, let us just let it be. Now we are moving. Is this clear?
Yes, ma'am. I have
Yes.
one doubt.
Yes, yes.
Can you scroll?
here.
In the where we made this xj omega. And when we have this xj omega already, so why we are doing this all thing?
We have xj omega, but we don't want xj omega. I want the Fourier transform of this signal. This is not xt now, so it will not be xj omega. And by our calculation, it turned out that there will be repeated copies of xj omega for this signal.
Yes, ma'am. After repeated copies, we are taking out the only one sample, right? So it will again we are getting that xj omega.
So what happens now? I have an analog signal. I want to transmit it. So I suppose I want to do something in my computer. So I have to convert it to digital. I cannot use analog. So the computation in computer that was done in digital. But suppose it was my sound. Now I want to hear it back after whatever processing I did. So I cannot hear my digital sound. To hear my sound, I need that analog signal. So that is why this digital to analog and analog to digital conversion is there, which we are doing here.
Okay.
This basically is, analog to digital conversion and digital to analog conversion. So according to whatever kind of signal we need, we do these conversions.
Yes, ma'am, that I understood. But if we already know the signal which we are going to get, so why not just take the xj omega as our signal?
So in communication, you will study if we transmit these low frequency signals, then there will be a lot of distortion, probably a lot of other things come into play. So we do something called modulation. So we convert this low frequency signal to a high frequency signal. So when we do all of these uh, computations or whatever you want to call, then this analog to digital and digital to analog, these things come, and getting back our signal from that high frequency things, all of those things come. So if you do a course in communication, you will understand that better.
Okay, ma'am.
Okay, so now we will move to Laplace transform. I will just quickly write the Fourier transform equations to see some kind of analogy. So Fourier transform x of j omega is equal to integration minus infinity to infinity xt e raised to the power of minus j omega t dt. This is the Fourier transform equation. Are you able to recall?
Yes, ma'am.
Inverse Fourier transform is xt is equal to 1 upon 2 pi integration minus infinity to infinity x of j omega e raised to the power of j omega t d omega. Now we are moving towards Laplace transform. Why do we need Laplace transform? Because we cannot find Fourier transform of every signal. Suppose we have a periodic signal with infinite energy, then we cannot use Fourier transform. And that is when Laplace transform comes into picture. So Laplace transform is used to analyze aperiodic signals with infinite energy. So what we do in Fourier Laplace transform is we convert the signal xt, which had infinite energy, to a finite energy signal. And how do we do that? Multiplying it by a decaying exponential. So I will just write it down here. We convert xt to a finite energy signal. And how do we do that? Xt multiplied by e raised to the power of minus sigma t. This sigma is some real number. So we say that this s is equal to sigma plus j omega, and this s is is the variable in the Laplace transform. So we define Laplace transform as x of s is equal to minus infinity to infinity xt e raised to the power of minus st dt. This is the Laplace transform equation. And how do we get it from the Fourier transform? So basically, Laplace transform is the Fourier transform of this signal. So if you substitute this instead of xt over here, you will get this, replacing sigma plus j omega by s. It is explained properly in the professor's lectures also. So this was the Laplace transform. Similarly, the inverse Laplace transform equation is xt is equal to 1 upon 2 pi j integration sigma minus infinity sigma plus infinity xs e raised to the power of st ds. So what we do, this is substituted here, then this exponential goes to this side, and then we use this substitution, and also this since we are converting this integration from omega to s, so we will have to use this df is equal to j d omega, or d omega is equal to ds by j, and that is how I get. And again, professor has explained it very nicely. Uh, so the equations are clear na, Laplace transform and inverse Laplace transform.
Yes, ma'am. One doubt.
Yes.
Ma'am, when we have the same type of equations, then why we are not able to find the for a periodic in the Fourier transform itself?
We are not able to find what?
Uh, we are not able to find the signal in Fourier transform by itself.
Are you saying that why we are not able to find the Fourier transform of this, but the Laplace transform of this?
I mean that in the Laplace and in Fourier we have a similar type of equation this formulas. So why we are not able to find the calculation of the signal xt in Fourier transform itself?
See, when we directly go to find the Fourier transform, then if the Fourier transform does not converge because of the infinite energy, so we cannot find that out, right? Dirichlet's conditions.
Yes, ma'am.
But Laplace transform, we multiply with this decaying exponential. Then we call this as to be this, and we just introduce a new thing, which is Laplace, which comes from this multiplying with this decaying exponential. So we just created one more transform.
Okay, ma'am, got it.
So these are the Laplace transform definitions. Now the next thing which comes in Laplace transform is region of convergence. Like in Fourier transform, we were just able to define it by this. But in Laplace transform, you will see we cannot define just by this. We need something called ROC in order to define the Laplace transform. So let us see what ROC is. ROC, or region of convergence. Region of convergence, or ROC. So now here we have also Laplace transform does not exist for any arbitrary thing. It exists only, I'm writing it down. It exists only for those values of sigma for which Fourier transform of xt into e raised to the power of minus sigma t exists. And that is defined by ROC. And the next thing to note is If ROC includes sigma equal to 0, then Fourier transform of that signal will also exist. So basically, ROC tells for which condition or which value of this S my Fourier Laplace transform will exist. So when we define a Laplace transform, we need the Laplace transform x of S and also its ROC. And if ROC includes this sigma equal to 0 line, then Fourier transform also exists. And another thing to note is ROC contains only strips parallel to j omega axis. ROC contains only strips parallel to j omega axis. I will give you one example for ROC. So we have this called something called as complex plane, or you can call it S plane. It has these two axes, real and the imaginary one. Suppose this is sigma equal to 1 line, this is sigma equal to 2 line. So S is sigma plus j omega. So real part of S is equal to sigma and imaginary part is equal to omega. So if this is the ROC between sigma equal to 1 and sigma equal to 2, then look at this some point somewhere over here. It can be expressed as A plus JB. Now, if in general we talk about this ROC shaded in green, then we can see that here B belongs to minus infinity to infinity, while A, the real part, is between 1 and 2 only. So we can say sigma belonging to 1 comma 2 belongs to ROC. Is this clear?
Yes, ma'am.
Now I will tell you what the ROC will be for some particular kind of signals. So let us quickly see that. So if xt is a finite duration and a bounded signal, then ROC for that xt will be the entire S plane. If xt is finite duration and bounded, and let us say it is bounded by capital M, then ROC will be the entire S plane. So this was number one. And number two, if xt is right-sided, this is clear now. First point, if xt is finite duration and bounded, then ROC is the entire S plane.
Yes, ma'am.
Now next is when xt is a right-sided signal. If xt is right-sided, and let us say sigma equal to A is in ROC, then sigma greater than A will also be there in ROC. So I will draw and show you what I mean. So suppose this is my xt. Right sided means it exists in the right side. So it is something like this. Now, this is my complex plane, j omega, and this is the real axis. And suppose this sigma equal to A is in ROC, then if it is right sided, na, then all this portion will also be there in the ROC. Is this clear?
Yes, ma'am.
Now the next one is when xt is left sided. xt is left sided and sigma equal to a is in ROC, then sigma less than a is also in ROC. So I will show it to you again. So left sided means something like this exists in the left side, and this is my complex plane j omega. So again, this is the sigma equal to a line, but here the signal is left sided. So ROC will be to the left of it. So all of this will be part of ROC. Is this clear?
Yes.
Now the fourth one is if signal is both sided. If signal is both sided, what does both sided mean? It extends from minus infinity to infinity. Signal extends from minus infinity to infinity. Then ROC is a rectangular strip. So I will show you the ROC here. This is my S plane. Suppose this is sigma equal to A, sigma equal to B. So if my signal is both sided, that is it extends from minus infinity to infinity, then ROC will be a rectangular strip like this. Now the things to note is ROC of right sided signal will be right sided, and so this was my right sided signal, and the ROC is also right sided. Are you able to see this?
Yes, ma'am.
Others, Sonali, Jay, Swastika, Rohit.
Yes, ma'am.
And similarly, ROC of left sided signal will be left sided. Let us see. Here, my signal was left sided. ROC is also left sided. Clear?
Yes, ma'am.
Now, let us solve two cases of Laplace transform to see the importance of ROC. First one I will do, second one you will have to do. So first we have to find Laplace transform of e raised to the power of minus at ut. That is, xt is e raised to the power of minus at ut. The Laplace transform formula minus infinity to infinity xt e raised to the power of minus st dt. I substitute xt. Now I will remove ut. So limits of integration will become 0 to infinity e raised to the power of minus at minus st dt. Let us take the e terms together. So minus a plus s t dt. The integration of this exponential comes out to be this, and the limits are 0 to infinity. When we substitute infinity, it goes to 0. When we substitute 0, we have 1 upon s plus a. So the Laplace transform of this is 1 upon s plus a I will leave some space to find ROC. First, you tell me the Laplace transform of this signal. Laplace transform of minus e raised to the power of minus at u of minus t. Take 2 minutes and quickly tell me what will be the Laplace transform of this. Class, you're solving now?
Yes, ma'am.
This is what you
Mama,
have.
when we are integrating it, so
Mhm. Yes, what happened?
I think I did wrong something. When we are integrating, we will get one like e to the power minus a plus st, and there we will have a minus infinity. So it will be minus into minus infinity, means it will go to infinity.
I was expecting you to solve this, but all right, let me quickly do it. So this is the Laplace transform equation. Is this clear?
Yes, ma'am.
Now let us quickly substitute xt over here. So xt here is minus e raised to the power of minus at u of minus t e raised to the power of st dt. If I remove u of minus t, then my limit of integration will become minus infinity to 0. This is the where u of t exists. This step is clear.
Yes.
Now let us take the e terms together. So e raised to the power of minus a plus s t dt. Now we will integrate. So the exponential comes as it is, and this is there in the denominator. The negative cancels. When I put t equal to 0, I will get 1 upon s plus a. And when I put t equal to minus infinity, oh, you're saying that it is going to infinity.
Yes, ma'am. I think it should be 80 only.
No, no, it should not be. So what is happening here? I don't know. It should have come out to be like that only. Did we make some mistake?
I don't think so.
So maybe I will clarify that on Monday. Let us first look at ROC, okay?
Okay, ma'am.
So if we find the ROC of the first one, so we had this integral, this one. I will just write it down. 0 to infinity e raised to the power of minus a plus s t dt. And we will break now s in terms of sigma plus j omega. So I have e raised to the power of minus a plus sigma t times e raised to the power of minus j omega t dt. This step is fine.
Yes, ma'am.
Now for this to convert converge, this this should be greater than 0, because if this thing is greater than 0, then overall it will be a decaying exponential in the interval 0 to infinity. So what I'm saying is the following: a plus sigma should be greater than 0 in order for this to converge, because only then this will be a decaying exponential. So this gives sigma should be greater than minus a. And what is sigma? Sigma is the real part of s. So real part of s is greater than minus a. So here the ROC is real part of s is greater than minus a. This is the ROC here. Is this fine?
Can you explain it to me
Which part?
from the starting?
Okay. So we went to this excess integral and we took this. Okay, and I just wrote it here as it is this fine?
Yes, ma'am.
Now in the next step, I write s is equal to sigma plus j omega and separate these exponentials like this. Is this
Okay,
clear?
ma'am.
Now next what I'm saying is that in order for this to converge, like if you see, this is like Fourier transform. Now here, if I want this to converge, then t is going from 0 to infinity. So that means it is on the positive side of the axis. So here, in order for this to converge, this exponential has to be a decaying exponential. Otherwise, it will not converge. It will instead go to infinity, right?
Yes, ma'am.
So for this to be a decaying exponential, a plus sigma should be greater than 0, right?
Yes, ma'am.
So sigma is greater than minus a. Sigma is the real part of s. So real part of s is greater than minus a, and this is the ROC.
Okay, ma'am. Got it.
Okay. Now similarly, we will calculate the ROC of the second one, and that integration I will confirm that on Monday. I will clarify that on Monday. So ROC of this, let us go to this step. So I will just write that same thing over here. Minus infinity to 0 e raised to the power of minus a plus s t dt. Again, I will write s as sigma plus j omega. So what I will have is e raised to the power of minus a plus sigma whole multiplied by t e raised to the power of minus j omega t dt. Now for this to converge here, for this to converge here, so this is in the time is going from minus infinity to 0, so it is on the negative side. So for on the negative side, for the exponential to converge, I want this.
Be less than equal to less than 0.
Wait, so this is e raised to the power of 80. A is greater than 0. This is e raised to the power of minus 80. Is this clear?
Yes, ma'am.
I mean, this is how the exponentials are. So now what we are dealing with is in this duration, minus infinity to 0. So here it will converge if there is this pink line. Otherwise, it will go to infinity. Pink one corresponds to e raised to the power of 80. So e raised to the power of 80, that is, it is a positive exponential. Sorry. Yeah. So this is positive. So basically here I want this overall one to be positive. So if a plus sigma is less than 0, then overall will become positive. So here a plus sigma should be less than 0 or sigma should be less than minus a. Is this clear?
Yes, ma'am.
So here ROC is real of s less than minus a. So actually now here also the Fourier transform should have come out to be this. So for these two cases, the Fourier transform is same, but the ROC differs. Here it was greater than minus a, here less than minus a. Is this fine?
Yes, ma'am.
Actually, on Monday also, now we just have 1 hour lecture only. So can we extend a little bit so that we could at least try to finish the week 11 summary today?
Yes, ma'am.
Okay, thank you. Just give me a minute, please. Now, the next thing that we have to discuss is pole zero plots. Suppose we have a rational Laplace transform x of s or rational x of s. It is rational, so it can be represented by a numerator and a denominator polynomial. Now, what are poles? So, poles are the roots of the denominator polynomial. Poles are roots of denominator polynomial. Number of poles, that is the number of roots of denominator polynomial, will be equal to the degree of the polynomial, right?
Yes.
And what will be the order of pole? So this is just the polynomial equations we studied. Roots is equal to degree and order is number of times that root is repeated in the polynomial. Order of pole is number of times that root is repeated in the polynomial. The polynomial here is d of s. The roots of denominator polynomial are poles, number of poles, order of poles, we have it. And similarly, the roots of the numerator polynomial will be known as zeros. So zeros are roots of numerator numerator polynomial. So roots of numerator polynomial are known as zeros. Number of zeros is equal to degree of numerator polynomial. Order of zeros, number of times that root is repeated in numerator polynomial. Is this clear?
Yes, ma'am.
Okay, now I will quickly give you one example. So suppose x of s is equal to s minus 1 upon s plus 2 s plus 1. So let us draw the pole zero plot for this. This is my s plane. So Can someone tell me what will be the location of first zero? The only zero.
1.
What will be the location of the zero? For zero, we have.
-2 and -1.
No, no, no. I'm asking for zero now. So zeros are the roots of numerator polynomial now. Here the
Okay.
numerator
1.
polynomial is s minus 1. So numerator polynomial is s minus 1. What is the root? S equal to 1. So where will be my 0 will be at 1. S equal to 1 over here. Similarly, the roots of denominator polynomial give me poles. So there are two poles here, two roots. So tell me the location of the poles.
-2 and -1.
Yes. So the poles are at s equal to -1 and -2. So this is how we draw the pole zero plot. Zero is represented by this circle and pole is represented by this cross. If there are multiple zeros, then you can, circle it like this and write like 3, 4, whatever the number of poles. Zeros are there, multiple zeros. Suppose there are 4. Do I do this? Suppose there are 5 poles. So this is how I represent. The representation is clear now.
Yes, ma'am.
And how to find poles and zeros? Zeros, roots of numerator polynomial. Poles, roots of denominator polynomial. Order, number of times that root is repeated. Can we move to the next topic?
Yes, ma'am.
Okay, so next is ROC of rational Laplace transforms. ROC of rational Laplace transform. So for rational Laplace transform, there are no poles inside the ROC. In fact, in rational Laplace transform, poles bound the ROC. There are no poles inside the ROC. For rational Laplace transform, there are no poles inside the ROC. Poles bound the ROC. So let us take xt to be right-sided. If my signal is right-sided, then ROC is all of the rightmost pole. I will just show you by a figure. Then ROC is the all of the right of rightmost pole. So suppose this is my S plane. Suppose I have poles like this. So what I'm saying is, if xt is right-sided, then which is the rightmost pole? These are the rightmost poles, right?
Yes, ma'am.
Others also, are you able to see that these are the rightmost poles? Sonali, Swastika, Jay. So if xt is right-sided, then ROC is all of the rightmost pole. So this is the ROC in this case. Now, if what happens if xt is left-sided? Let us see. If xt is left-sided, then ROC is the all of the left of leftmost pole. So a few minutes back we said na that ROC of a right-sided signal is right-sided. So this we can see here also. And for left-sided, the ROC should be left-sided. We will see that here. So what this says is, if XT is left-sided, then ROC is all of the leftmost pole. Are you able to see that these are the leftmost poles?
Yes, ma'am.
So ROC is to the left, all of the left. So this is my ROC if XT is left-sided. Now what happens if XT is two-sided? That is, it extends from minus infinity to infinity. If xt is two-sided, then ROC is a strip between the rightmost pole and leftmost pole. If xt is two-sided, then ROC is a strip between the rightmost and leftmost poles. So in the example that we are taking, we will have two possible ROCs. I will show you. So it is a strip between the rightmost and leftmost poles. So basically, inside ROC, I cannot have any pole. Zero can come inside ROC, but a pole cannot come inside ROC. So here there are these two possible ROCs. Like this is one of the possibility. This is another possibility. So if signal is two-sided, ROC is a rectangular strip, and these are the two things possible because a pole cannot come inside ROC. Here also the pole did not come inside ROC, neither here. And my signal was left-sided, ROC is also left-sided. Are you able to see this?
Yes, ma'am.
Okay, now next is geometric interpretation of pole zero plot. This is our next topic, geometric interpretation of pole zero plot. So the frequencies which are farther from the pole and closer to the zeros are attenuated. Frequencies farther from the poles and closer to the zeros frequencies closer to the poles and farther from the zeros are amplified. So what I'm saying is, suppose this is my transfer function. So this what is a zero over here? S equal to 1 is a zero here, right?
Yes, ma'am.
So if I put s equal to 0, what will be the amplitude of, what will be the magnitude of excess at s equal to 1?
0.
It is 0. So we can say that 0 drives the amplitude towards 0. And let us take a pole. So let us take this pole s equal to -2. If I put s is equal to -2, what will be the amplitude of x of s?
Undefined.
Infinity, it will go to infinity. So what we can see is 0 drives my amplitude towards 0, while poles drive my amplitude towards infinity. So that is from where this is coming, that frequencies farther from the poles and closer to the zeros are attenuated. Closer to zeros, so it will come close to 0, attenuated. Frequencies closer to poles, if they're closer to poles, amplitude is driven towards infinity. So we can say that they are amplified. So again, I will repeat these statements. Frequencies farther from the poles and closer to the zeros are attenuated. Frequencies closer to the poles and farther from the zeros are amplified. Is this clear?
Yes, ma'am.
Now the last topic, Bode plot. Then we can end the class. So in Bode plot now, we suppose I have this x of s transfer function. So in Bode plot, I can represent a magnitude and also the argument. But the what has been discussed here is the plotting of magnitude, and magnitude that also we will plot in dB. So this is the absolute magnitude, and when we take it in dB, it will become 20 log 10 this. So this is what will convert this to dB. Is this fine?
Yes.
Now I'll quickly summarize things from the lecture. So at
Ma'am,
the
is there any derivation for this body plot or it's just like this?
I mean the derivations are there for the points that I will be telling you, and sir has I think derived that.
Okay, ma'am, we'll look into it.
What?
Okay, we'll look into it.
Did you not see the lecture?
I watched 5 lectures.
Okay. See, since your end terms are near now, so we are trying to finish everything quickly so that you get some time for revision also.
Yes, ma'am. But I have OPP also, so I have to focus on that.
Okay. So uh, when we're talking about Bode plot, so at a 0, amplitude increases by 3 dB, and at a pole, amplitude at a 0, amplitude was increasing. At a pole, it is decreasing, and by the same amount. So I will just draw a figure and show you. This is the amplitude in dB. This is 10 raised to the power of 0. I have a 0 at the frequency 10 raised to the power of 1, and a pole at frequency 10 raised to the power of 2. These are in radian per second. Suppose this is how, just a minute. Yeah. So suppose this was my initial amplitude. So now as I come closer to 0, there will be this 3 dB increase in the amplitude. Then it will be like this. Now I come at a pole. So it will go down by 3 dB and continue. So this is 3 dB. Here I had a 0, so it increased by 3 dB. I had a pole, it decreased by 3 dB, and finally it is at the same value. Is this clear?
Yes, ma'am.
Okay. Just give me a minute, please. Now, when we draw Bode plot, na, so at zeros and poles, the slope of the plot changes. So how does it change? That is what I will be writing over here. So at 1 0, slope increases by 20 dB per decade, and the derivation professor has done. So at 1 0, slope increases by 20 dB per decade. Okay, what is decade? My frequency was 10 raised to the power of 0. It goes to 10 raised to the power of 1. So this is 1 decade. 1 decade means increase by a factor of 10. 10 raised to the power of 1 going to 10 raised to the power of 2. Increase by 10 times. This is 1 decade. So 1 decade is increased by 10 times. Is this clear?
Yes, ma'am.
So what this 20 dB per decade means is, in this magnitude plot where the magnitude is in dB and the frequency is in radians, so my slope will increase by 20 dB for 1 decade. That is when the frequency becomes 10 times. Is this clear?
Yes, ma'am.
Now similarly, if I have n zeros at the same location, multiple zeros, n zeros at same location, like here instead of one I had two or maybe three zeros. So in transfer function it will correspond to this. So how many zeros I will have? Three, right? Class, is this clear that this will have it will have three zeros at s equal to 1?
Yes, ma'am.
So this is what I mean. So if I have n zeros at the same location, then slope will increase by 20 times n dB per decade. Similarly, for poles, it will decrease by the same amount. So at one pole, slope decreases by 20 dB per decade. At zero, it was increasing. So if initial slope was zero, then at once we encounter 1 0, slope will become 20. Now if I encounter another pole, it will decrease by 20. So it will go back to 0. So at one pole, slope decreases by 20 dB per decade. And similarly, n poles at the same location, slope will decrease by 20 times n dB per decade. So the meaning of decade I already explained you. So let us just take one example. This is omega, which is in radians per second. Here, suppose I'm calling my transfer function h of s. So it is there in dB, that is 20 log mod of h of s. So is it clear what are the quantities there in x and y axes?
Yes, ma'am.
Suppose here I have 10 raised to the power of 0, then 10 raised to the power of 1, increasing by a factor of 10. Now say I have poles and zeros at these locations. 0 over here, one pole, another pole, another 0. Suppose this was my initial slope, which was 0. So now I encounter a 0. If my initial slope was 0, what will my slope become now?
20 decibel.
Yes, 20. So here slope was 0, here it is 20 dB per decade. Now I encounter one pole. So my slope will decrease by 20. So I will have 20 minus 20, which will give me 0. Is this clear?
Yes, ma'am.
Now I encounter another pole. So what will happen?
Minus
Another,
20.
yes, 0 minus 20 will give me minus 20. Now I encounter one 0. So minus 20 plus 20 will give me 0, and then it will go on like this. So this is a magnitude Bode plot. Is this clear?
Yes, ma'am.
And that this thing that we talked about, 3 dB increase and decrease. So if we show that now, then there will be this slight increase over here, slight decrease, slight decrease, slight increase. So that was very small, so we just we did not consider it. Is this fine?
Yes, ma'am.
Okay, so now if you look at this magnitude plot, which kind of filter does it look like? You know the types of filter, na? Low pass, high pass, band stop.
Band pass.
Yes. So this is a band pass filter. It is passing this band of frequencies, and here the amplitude is 0, so they are attenuated. Now, if I want this to be more sharper transition, like maybe like this, as much as I can get. So I will have to add 0. What happens? Suppose okay, I will first write that down. To increase slope, add zeros, and to decrease slope, add poles. So if there's a 0, the amplitude was 0, it goes up. If it was 0, there's a pole, it goes down. This is clear now.
Yes, ma'am.
Now let us see. If I want this to be more sharper, what I can do, maybe I'll add one more 0 here. Then my slope will increase by 20 into 2 dB per decade. So my slope will become 40. Are you able to see this?
Yes, ma'am.
If I add one more, what will my slope become?
60.
Yes. So if I keep on adding zeros, this transition is going to get sharper. So I will get more slope. Is this clear?
Yes, ma'am.
So I will get a much better band pass filter because the slope sharper it gets, the better it is, right? Is this clear, class?
Yes, ma'am.
Yes, ma'am.
Now, similarly, if I want to make this sharper, so I need to have something like this, right? Class, are you able to see this?
Yes, ma'am.
So we will add more poles, so it will decrease more rapidly. Are you able to see this?
Yes, ma'am.
Okay, so that's all I had to discuss from my side. On Monday, we will solve problems based on week 11.
Okay.
Does anyone have any doubt? Okay, so thank you for joining. Have a great day.
Thank you, ma'am.
Thank you, ma'am.